For number 6, we have the resistance of a copper wire carrying an electrical current is directly proportional to its length and inversely proportional to its cross-sectional area. Okay, let's write that down. So resistance, I'm going to call that R. So R is directly proportional, so that means it's K times something to its length, so we'll call that L. And inversely proportional, so remember that's K divided by something, to its cross-sectional area. I'm just going to call that A. Okay, so that's the relationship we've got going on. So given that a number 28 copper wire has a diameter of 0.0126 inch, has a resistance of 66.17 ohms per 1,000 feet, what length of copper wire will produce a resistance of 33.5 ohms? Okay, we're going to need to plug in some stuff here. So let's see. Resistance of 66.17. That we can plug in. That's clearly R. We don't know what K is. That's what we're trying to find out. And L, how long is this wire? It's 1,000 feet long. So K times 1,000. And then we have the area. This is the cross-sectional area of the wire. So area is pi r squared. Our diameter is that. So we need to cut that in half to get our radius. So, I don't know. Well, I could just write it this way. We can do it in our calculator later. So we're going to take 0.0126 and divide it by 2, and then we'll square that. Okay, so now that we've plugged everything in, we need to solve this for K. So we're going to multiply both sides by the denominator. I'm not going to write out all this work because my handwriting's terrible today. So we'll do 66.17 times pi times parentheses 0.0126 divided by 2 squared, and then you'll divide both sides by 1,000. So when you do that, we get K equals, it's a lot of zeros, 5 zeros. 1, 2, 3, 4, 5, 8. Okay, so there's K. So now we know that our resistance is 8 L over that cross-sectional area. Okay, that's our model. Now, they wanted us to find something else out. What length will produce a resistance of 33.5 ohms? So we want to plug in 33.5 ohms. 1, 2, 3, 4, 5 zeros. We're looking for length. And our area, our cross-sectional area is still the same because we haven't changed what type of wire we're using. So it's pi r squared. So remember, you have to divide that diameter by 2. I can't put a decimal there. Okay. And again, you're going to solve both of those. Solve that pink equation here for L. So you'll do 33.5 times pi and then this whole mess squared, and then divide everything by 0.000008. And we find that L is, I don't really have a place to write it. L turns out to be 522 feet. Okay. All right, one last of these. The kinetic energy of an object varies jointly with the object's mass and the square of the object's velocity v. So let's write that down. Kinetic energy E varies jointly. That means there's two things. So K times two things. The object's mass and the square of velocity. So velocity squared. So that's our equation. Okay, now we don't know what K is. Remember, it's a constant. We'll have to figure it out. An object with a mass of 50, so we can plug that in here, 50, traveling at 16 meters per second. That's its velocity. We don't know what K is, but it has kinetic energy of 6,400 joules. So you just use your calculator, solve that for K. I'm going to kind of skip those steps, and we find that K is 5. So going back up here, our new equation, Our model is E equals 5mv squared. Now, if they're asking you for the model, you would be done, but they're not. They're asking, what is the kinetic energy of an object with a mass of 70 when it's traveling at 20 meters per second? So we want to know the energy of mass 70 at 20 meters per second. So we're just going to plug those things in, use our calculator to find our energy is 140,000 joules.